All right. We're going to try to understand the solution of equations now. Now that we know how to find the solution to a system of equations, we need to try and understand the system of equations. And that means I need to introduce the third way of solving a system of equation, and that's graphical. So you can solve it by the method of elimination and the method of substitution. Those are two algebraic methods. When solving an equation graphically, we find the point where the equations meet. Let's go back to that first example again, one last time. I got 2x plus y equals 1, and I have x plus 2y equals 2. Now, if I want to graph the line, I need to put in point slope form. And so what I would need to do is I need to subtract 2x on both sides, correct? And so that will give me that y is equal to negative 2x plus 1. The slope m is equal to negative 2 over 1, and the y-intercept is equals to 1. Yes? Over here it's a little bit harder. Over here on the other side, I got to subtract x on both sides. So I have 2y equals negative x plus 2, and I got to divide by 2. So I get y is equal to negative 1 half x plus 1. And so that's my equation right here. Y equals negative 1 half x plus 1. The slope m is negative 1 over 2. And the y-intercept equals 1. So if I was to graph these two lines, well, the first line has a y-intercept of 1 and a slope of negative 2 over 1. So I'm going to go down to 1, 2, and then over 1. And so this is going to be my first line. Y equals negative 2x plus 1. And then my second line, I have a y-intercept at negative 1, at 1. And then my slope is, I go down 1 and over 2. And so my second line looks like this. It's obvious, but that's why I chose this example. The point where the two lines meet are 0, 1, which is the x and the y answer we got when we worked this problem out early on. And so, graphically speaking, the solution to a system of equations is where the two equations meet graphically. So how does that help us understand our equations of our graphs? Well, when we're solving our equations of a graph, we have different types of solutions based upon how the graphs interact. So you have your first, we have what's called the consistent and independent solutions. The consistent and independent solution is one where you have two graphs that simply meet at one spot. And so you have one spot right here. They have one ordered pair of solutions. That is, you get one answer. If you look at them graphically, they will look like intersecting lines. Lines that meet once. And then the third thing right here is that the two lines must have different slopes. Look at the two examples we've done before. This line clearly has a positive slope, while this line down here has a negative slope. The slopes will be different. That's the first kind of solution that we get. The second side is what we call an inconsistent system. In the inconsistent system, what happens is that the two lines of the graph, they never meet. And because they never meet, they have no point of intersection. If they have no point of intersection, then we have no solution. Which is really sad. Lines do not intersect. If you know anything about algebra, about geometry rather, you'll know that parallel lines okay? Parallel lines, in parallel lines right here, but a special kind of parallel lines with different y-intercepts. Once you have that happening, you have an inconsistent solution. The last thing about your inconsistent solutions is that the slopes will be the same. Parallel lines have the same slope. When you have that happening, you have an inconsistent system. No answers, no answers. The last possibility, let's look at an example of a system that is inconsistent. So let's say I have x minus 2y is equals to 6 and negative 2x plus 4y is equals to 6. I didn't do an example of a consistent system, consistent and independent system, because we've done two of those already. But in this system right here, if I go ahead and I solve this equation, I will get something that's simply impossible. So let's say, for instance, I solve for y. So I have that x is equals to 2y plus 6 if I add 2y to both sides. Plus 2y plus 2y. And then I substitute that into for x. I get negative 2 times 2y plus 6 plus 4y equals 6. I distribute. I get negative 4y. I distribute. I get negative 12 plus 4y equals 6. And look at that. The 4y's will cancel out. And after they're cancelled out, I get this. 12 is equals to 6. This is simply not true. And when you get a statement that's not true, based on your equal sign, the system is inconsistent. It has no solution. Negative 12 is simply not equal to 6. The last kind of system that we get is a consistent but dependent solution. By the way, when we say consistent, it means we have an answer. We'll get to the independent versus dependent in a second. The consistent but dependent system is one where the two lines that make up, the two graphs that make up the system are exactly the same graph. When you have that lying one above each other right here, you ask yourself, well, how many times do these graphs meet? Well, these graphs will always be meeting, right? At this point right here, they're meeting. At this point right here, they're meeting. And this point right here, they're meeting. But it's going on forever. So the first feature of these graphs right here is that they have an infinite number of solutions. Which is interesting, by the way. How do you write an infinite number of answers? And if you look at the graphs, we will see what we have is overlapping lines. We have the same line on top of each other when you graph the two equations. You're solving graphically. And they will have the same slope. And they will have the same y intercept. When we have that right here, we have a system that is said to be consistent because we are getting solutions, but dependent in that it's dependent when we look. If I look right here, I get one answer for x and y. You have x and you have y. If I look over here, I get a different answer for x and y. But there are an infinite number of pairs of x and y that gets us to the answer. The thing you have to remember is that when they say an infinite number of pairs, it doesn't mean any pair will work. Like for instance, right here, let's say that's 5 and let's say that's a 2. 5, 2 does not work for the system. It has to be a pair of numbers that lie on the line that give us our answer. Excuse me? Let's look at an example of a consistent but dependent solution. When you're working with a consistent but dependent solution, say I have 2x plus y is equals to 2, and I have 6x plus 3y is equals to 6. And so let's eliminate the y's. And so I multiply this equation by 3, and I multiply this equation down here by -1. And in so doing, I get 6x plus 3y equals 6, and then multiply by -1, -6x minus 3y equals -6. If you look very carefully, you'll notice that I have the same exact equation, but with opposite signs. When this happens right here, both of these eliminate, so leaving me with 0, and on the other side, it leaves me with 0. Well, if 0 equals to 0, yes, this is true. And that's why it's a consistent solution, because 0 does equal 0, unlike our previous example, where we got -12 is equals to 6. So it is a consistent system. In solving this equation, both x and y got eliminated, both x and y went away, and when you have that right here, you have what's called a dependent solution. Dependent solution. And all this means is that to get an ordered pair, I have to pick one variable and then solve for the other. So right here, your dependent solutions, they're always written as an ordered pair that looks something like this. You let one of your variables be quote-unquote free. So I just have y just by itself. And then I say where y is a number. And then I go to one of the equations and I solve for y. So I get 2x plus y equals 2. Subtract the 2x over. So y is equals to, solve for x actually. And so I'm going to go ahead and take the y over, so 2x equals -y minus 2, and then divide by 2. And so I get that x is equals to -1/2 y minus 1. -1/2 y minus 1. That's going to be the value of x. So as I choose different numbers for y, I will get a different ordered pair. Since there are an infinite number of numbers that I can choose for y, I will get an infinite number of ordered pairs. And so this system right here has an infinite number of solutions.